Good afternoon, ladies and gentlemen. Today we're privileged to have with us Dr. Carolyn Porco, who is the leader of the imaging science team on the Cassini mission, and she is also an imaging scientist for the New Horizons mission, which is also a post that she held as well for the Voyager mission. She's received her doctorate degree from the California Institute of Technology in the Division of Geological and Planetary Sciences, and she's a tenured faculty member with the University of Arizona. She's the editor and creator of the Cassini team's Cyclops website, which is where you can view images from the Cassini mission. And she's also the CEO of Diamond Sky Productions, a small company dedicated to the artful and useful use of planetary images. Asteroid number 7231 is named in her honor, and she's responsible for sending the cremains of renowned planetary geologist Eugene Schumacher to the moon. Please join me in welcoming Dr. Porco.
Thank you very much. Is there any way we can lower the lights in this room? Because the pictures will look so much better if the lights could be lowered. Thank you, Leslie, for that introduction. I just want to say I've been, ever since the TED conference, I don't know if you guys know about the TED conference. You must, because it sort of happens in your backyard, where I met Larry and Sergey, and I got invited to come to give a talk here. I've been really looking forward to coming here, and this place is kind of legendary. The cafes are legendary, and I've now sampled the cafes. I know what that's all about, and there's something I know is going to be legendary soon, and I just sampled it, but I never knew about it, and that is your heated toilet seats. You do realize the rest of the world doesn't live like that? Okay, and I can tell you that's one perk you're not going to find at NASA. So anyway, it's a thrill. It's even more of a thrill than I thought to be here. I feel that I have lived a charmed existence to have grown up during a time when I did. I was a young girl when our country became a spacefaring nation, and images from the moon and Venus and Mars were being sent back to Earth and being published in the newspapers of New York, which is where I grew up. I was a teenager when Neil Armstrong first walked on the moon in 1969. I was a young graduate student when the Viking spacecraft landed on Mars in 1976. And I was a senior graduate student when the Voyager spacecraft first flew by Saturn in the early 1980s. And a newly minted PhD, I became a part of the Voyager imaging team in 1984-83 and participated in our first reconnaissance of the planets Uranus and Neptune. And now I'm extraordinarily privileged to be part of one of the most dazzling interplanetary endeavors we have ever undertaken. And I've got, as far as I'm concerned, the best job in the whole inner solar system. I am the leader of the imaging team on Cassini. We are responsible for taking all those lovely images of Saturn that you've seen over the last several years. And these missions of exploration that humankind has been undertaking for the last 50 years, I think you would agree, are all part of a much larger human quest or human voyage to come to understand something about our origins and how our planet and we living on it came to be. And one of the most promising places we could hope to explore in our solar system in answer to those questions is the Saturn system. Because Saturn, with its complex systems, subsystems, if you will, of atmosphere, magnetosphere, rings, and moons, all interacting, provides the ideal destination for studying many of the same physical processes that planetary scientists today believe were responsible for the formation of the solar system and are responsible and ongoing today for the present-day dynamics of our solar system and solar systems around other stars that are being discovered in our galaxy. So aside from offering splendor and beauty beyond compare, Saturn is one planetary system whose exploration offers enormous cosmic reach. We, of course, had been to Saturn with the Pioneer spacecraft and the Voyagers in the early 1980s, but our investigation of this planetary system began in exquisite detail when, in the summer of 2004, the Cassini spacecraft flawlessly glided into orbit around Saturn and became, at that point, the farthest robotic outpost that humanity had ever established around the sun. And for me, our return to this particular planetary system is not only part of but also a metaphor for that grander human voyage to come to understand the interconnectedness of everything surrounding us. So I'm thrilled to be able to tell you this afternoon, to take you, show you how this particular leg of this voyage, this grand voyage, through the Saturn system, as Cassini is revealing it to us, is how Saturn and everything around it has been shown to us over the last 1,000 days that Cassini has been in orbit. And to give you a sense, and a decidedly visual one at that, for how this very major exploratory expedition that Cassini and we are presently conducting around Saturn is unfolding. The first obvious example of cosmic reach, of course, are Saturn's rings. They're the reason why Saturn is the icon it is among planets in our solar system. The rings are a tremendous visual spectacle. They are 280,000 kilometers across. That is about 1 light second. They would fit in nicely between the Earth and the Moon. And they consist of countless orbiting bodies. This is ice particles ranging in size from the finest snow you might ski on in Utah all the way to the sizes of small apartment buildings, screaming around Saturn at tens of thousands of miles per hour, yet only very gently jostling each other. They only collide if and when they do at a few millimeters per second. They are what physicists call a very equilibrated system. Any violent collisions in this system died out a long time ago. And because of that, they are tremendously thin. They're only 1, 2, 3 stories in a modern day building. They're paper thin. They trace out, they're very mathematically precise. They trace out the plane of gravitational equilibrium around the planet. And despite their visual enormity, they contain, in fact, comparatively speaking, very little mass. If you took all the mass in Saturn's rings and recomposed it back into a small moon of the proper density, it would be no bigger than this little moon here, Enceladus. So a lot of visual display for very little mass. Is there a laser pointer I can get a hold of? Somebody? Okay, the processes that are ongoing in this disk. Okay, that one, thank you. There's 47 buttons on this. I hope I hit the right one. By the way, these are the shadows of the rings cast on the northern hemisphere of the planet. And the processes that are ongoing in this disk of material are believed to be similar or identical to the ones that went on in the nebula from which the sun and the planets form. This is shown here in this artist's rendition. And in disks that we are presently seeing around other stars. This is a Hubble Space Telescope picture of a proto-stellar disk around a very young M-dwarf star, and then reaching 1 trillion times larger. The same processes we see going on in Saturn's rings occur in the disks of dust and gas and stars that are the spiral galaxies. So there is a great deal to be learned in studying Saturn's rings about disk systems all throughout the cosmos. And in this sense, what we are learning and hope to learn further with Cassini is truly universal. The rings exhibit an enormous variety of structure, discovered a long time ago when the Voyagers first flew by. We didn't understand where most of it came from, and we're only now getting glimmers of it with Cassini. They break down, some of you may already know, into 3 main elements. This is the A, the B, and the C ring. The B ring is the most massive. It's the densest. It casts the deepest, darkest shadows on the planet. It's where a lot of this structure is that we are having a hard time understanding. The A ring is a little bit more transparent, is punctuated by gravity-driven features that are driven by the gravity of orbiting moons. And then here is the C ring, which is very diaphanous and is actually populated by these very sharp-edged plateaus of material. Again, we don't know exactly why. We don't know, in fact, at all why those plateaus exist. And so the subtle colorations you see here are due to the contamination of basically what is water ice by very small amounts of other materials. And we're in the process of working out what the compositions of that material, what the composition is. So Saturn is as you know, very far away. It's 10 times farther away from the sun than the Earth is. And the Cassini spacecraft at launch was very massive. It was 6 metric tons. And even launching Cassini on the largest launch vehicle that we had at the time, which was a Titan IV, adding solid rocket motors to it, strapping those on, and putting Cassini on top of a Centaur upper stage, this was about as much power as we could throw at the thing. That still wasn't enough to get Cassini, because it was so massive, directly to Saturn. So we had to loop it around the inner solar system twice. We had to send it by Venus twice. We had to send it by the Earth once. And then finally, on the eve of the year 2001, which I thought was tremendously poetic, we sent it by Jupiter for a final push on to Saturn. Now, understand that the object of this exercise is to get the spacecraft to its target as quickly as possible so that those of us who are involved in the mission are still alive by the time the spacecraft gets there. But that means that by the time it gets there, it is hauling. Okay, and we actually have to slow it down in order to allow it to get captured into Saturn orbit. And that was done in a 90-minute maneuver, shown here in an artist's depiction, where we basically threw the engines in reverse. Actually, we didn't do that. We just turned the spacecraft around, and we burned half of the mass at launch of Cassini was fuel that was burned in this maneuver to slow it down. Okay, we didn't slow the speed down. We actually slowed the acceleration down to allow it to get captured into orbit. And so this maneuver brought us closer to the rings than we had ever been before. We'll ever get again, very likely never be as close as we were during this maneuver ever again in the course of the mission. And so the scientists for years were clamoring to be allowed this opportunity to take data when we were cruising over the rings. And that's in fact what we did. We collected a beautiful collection of images of the highest resolution we've ever had on the rings. And we saw many things. I don't have the time to show you all of them. One thing we saw a lot of was waves. In this picture, the smallest thing you could see, the tiniest little pixel there, is only a couple or several hundred meters, so just several football fields, okay? These are waves. These are the fingerprints of orbiting moons that are perturbing the ring particles. You see here something called the density wave. This is where the perturbed non-circular orbits of the ring particles are all phased in such a way as to give rise to these regions of higher than average concentrations of particles, which in fact spiral all the way around the planet. These are spiral density waves. We're looking incidentally on the dark side of the rings, so what you see here is dark is actually bright if you saw it on the lit side. So the highest concentration here are the dark regions. They spiral around the planet. These are the kissing cousins of the spiral arms you see in galaxies. Same mathematics. It was co-opted from galactic structure, the physics of galactic structure, and applied to Saturn's rings to in fact predict that when Voyager got there in the early 1980s, it would find these features. And in fact, it did. With Cassini, we got just a very much better look. These are bending waves. These are the vertical equivalent of density waves. This is where it's not the eccentricities of the orbits that are perturbed, it's the inclinations. And so this is a feature where there are crests. This is like corrugated cardboard. The whole ring plane is warped like corrugated cardboard, and the crests spiral around the planet. Okay, again, these are due to the perturbations of orbiting moons. This was on the dark side. When we crossed over the rings and passed onto the lit side and then turned around and looked up at the rings as we were receding, we saw these kinds of things. Lower resolution picture by about a factor of 3, but still you could see lots of waves, lots of waves. You even see this thing, corduroy structure. This is the perturbations of a moon orbiting actually within the rings. So lots of phenomena we got a very good look at with these pictures. And one remarkable and very telling discovery we made in this collection of images are these little propeller features. Okay, these are the beginnings of gaps that are being made in the rings by bigger than average particles. They're about several kilometers across, a few hundred meters wide. The pixel scale here is the highest it ever got for us. This is like a half a football field per pixel. And so from the dimensions of these features, we can tell the size of the bodies that are making these incipient gaps, and they look to be something like 20 to 60 meters in radius. So that is a little bit bigger, several times bigger than the largest particle size. Okay, and this one observation has given us insight into the particle size distribution in the rings, and also will eventually tell us something about the way the rings evolved. But there are even bigger bodies that are embedded within the rings, of course, and they're having dramatic and more obvious effects on the rings. This is the A ring. This is the famous F ring that is shepherded by two shepherding satellites called Prometheus and Pandora. This gap is called the Encke gap. Keep this gap in mind. This is called the Keeler gap. I'll show you this later. This gap is about 300 kilometers wide. It is inhabited by a moon called Pan. Okay, and the next picture, these, by the way, are all those density waves that are created by other moons orbiting Saturn. The next picture is going to show you a high-resolution view of this that we got during the Saturn orbit insertion maneuver. And there you see it. It's so beautiful it looks simulated, but it's actually a real image. There are ringlets in this gap. Remember, this is 300 kilometers wide. These are waves in the edges of the gap that are created by the perturbations of Pan. It excites eccentricities in the orbits of the particles in the rings. And those eccentricities, again, they're all properly phased, that they give rise to this pattern. You can see the streamers spiraling away from this edge. Also, again, the perturbed motions of particles, the perturbed and phased motions of particles. And here's a view we got later on in the mission of Pan. This is the culprit. This satellite is about 30 kilometers across. The rings are only a few tens of meters, so you can see it protruding up and down. It's a beautiful picture. It was very thrilling to finally get a close-up view of Pan. We also looked closely at the Keeler gap, which is 42 kilometers across, and we discovered Daphnis. This is a little moon, only 8 kilometers across. It's doing the same thing on the edges of its gaps. It's raising waves. And the study of these systems, a moon in a gap in a disk of material, though I should say these systems provide the best analogs we have available to us in our solar system for the systems that are being discovered nowadays every day. That is, growing planets or protoplanets in stars, in disks around other stars. And the study of the manner in which these bodies, like Pan or Daphnis, open up a gap in their disk and keep the material at bay through their gravitational interactions is going to prove very fruitful for the study or for investigations concerning planet formation, understanding how, for example, Jupiter, a planet like Jupiter, growing out of the solar nebula, accreting material little by little, getting bigger and bigger, finally comes to get so big it truncates its own growth by opening up a gap. Now, one of our main objectives was also to determine the physical characteristics of moons that were orbiting near the rings, and also to the physical characteristics of any moons that we might discover, because we were suspecting that their physical characteristics would tell us something about their origins. And that's, in fact, exactly what we've done. This work has gone on in my group in Boulder, Colorado. And let me first pause here and tell you our general notions about how rings come about, in case you don't know. The common wisdom says that there was a body, very likely a pre-existing moon in orbit around Saturn, that got bashed up by an incoming projectile. And that material eventually spread out to form a ring. It's just a simple, predictable physical process. It spreads out to form a ring. There are collisions. The collisions are very elastic. They grind down the particles, but they also flatten the system into a ring. Okay, a ring that is, as I said, inhabits the equator plane of the planet. Okay, another idea is that the progenitor body that forms the rings maybe came in from afar. Maybe it was a body that came in from the Kuiper belt. But anyway, the idea is a catastrophic disruption of a pre-existing body. Material gets swept up and encircles the planet. Well, over the last 3 years, we've accumulated enough information on the ring moons, like Pan, like Daphnis, and also like Atlas. This is a body orbiting outside the outer edge of the A ring. This is the Keeler gap. This also is about the size of Pan, 30 kilometers across, looks like a flying saucer. And also Pandora. This is bigger, 81 kilometers across. This is one of the F ring shepherds. Okay. We have now information on the sizes, the shapes, the orbits of these bodies, even their masses and their densities. And putting all this together, we have found that these bodies are shaped like you would expect for a body formed by accretion. So in and of themselves, they are not the remnants of this collision that formed the rings, but we think instead that they have grown around a denser core, and that denser core may be something that dates all the way back to the original creation of the rings. So we're getting glimpses of the chronology of events in the Saturn ring-moon system from Cassini so far. And speaking of moons, Saturn is accompanied by a very large and diverse collection of them. Now there's something like 57 moons. There may even be more, because I only looked about a month ago. They're being discovered all the time. They range in size from a few kilometers across to Titan, which is Saturn's largest moon. It's as big across as the US. And it's the inner collection of moons, which go out to only a few million kilometers from Saturn, that is the system that's being investigated by Cassini. And this system is of particular interest because it is believed, because these moons are all in orbit in the same plane, they're all orbiting in the same direction around a big, massive central body, they are like a miniature solar system. And so our goals in studying the Saturn satellite system, this particular component of it, were not only to come away with accurate measures of their compositions and their physical characteristics, not only to further our understanding of their geological histories and their thermal histories and so on, but also to study the system as a whole with an eye towards testing our ideas about planetary formation, both the formation of our own planets and others we are discovering today. Now, the Cassini tour through the Saturn system is unprecedented. It's enormous in magnitude, calls for 82 close satellite flybys within 4 years. All of them are closer than the flybys that were conducted by Voyager. 44 of those are of Titan alone, and the remainder of them were flybys of this handful of medium-sized moons that are, as I said, within a few million kilometers of Saturn. And some of these flybys were exquisitely close. They flew as close to these moons as the space station flies above the Earth. And most of these exquisitely close flybys were conducted in the year 2005. I call that the year of the moon. That's when we came up close and personal to all of these and have come away with have discovered some remarkable things about their geologies and physical characteristics. And we've certainly, if you've been paying attention, seen that we've returned some fantastic images. This is Tethys, a moon that's about 1,000 kilometers across. That's about 600 miles. Sports some amazing basins on its surface. It's shown with the rings in the background, one of our beautiful images. This is Rhea, 50% bigger than Tethys, so 1,500 kilometers across. That's about 1,000 miles. Okay, so we're talking about something maybe the size of the southwest US. This is Rhea hiding behind the rings. This is one of our beautiful pictures of Dione. This is about the size of Tethys, again, about 1,000 kilometers across, seen against the globe of Saturn with the rings in the foreground. Here's another view of Dione, okay, taken at very high phase angle as the sun was either rising or setting, I don't remember. And then here's a close-up of that. Okay, now I don't know about you, but this calls out for an astronaut, doesn't it? Don't you want to see an astronaut walking across the surface of that? Actually, you wouldn't be able to resolve an astronaut because the smallest pixel here is about 100 meters, so that's about a football field across. This is actually a very big, very large crater. And then here's our Death Star moon, Mimas, okay? 2.5 times smaller than Dione. And then smaller again, about 2 times smaller than, or half the size of Mimas is Hyperion, looking like a great cosmic sponge. And then finally, I'm going to show you Iapetus. Iapetus is a moon that's half the size of our moon. It's about the size of Rhea, 1,400 kilometers across. And we have found some fantastic geology on Iapetus, as you can see. This is the moon that's half black on one side, half white on the other. black and white. And here you can see this amazing landslide at the bottom of a 15-kilometer high cliff. Okay, so it's not out of the question in my mind that someday your descendants might be taking extreme excursions into the Saturn system and ice climbing on the cliffs of Iapetus. And I envy them. I should say that all of these moons are made out of water ice. That's the most abundant material in the Saturn system, in the Saturn satellite system. And water at these temperatures is a rock-forming mineral. So they're mostly water ice. Now, you don't have to look too far, on, or I should say, all you have to do is look at the cratered surface of these bodies to know that there was a time many, many years ago, in the early history of the solar system, when there were a great many bodies careening around the solar system and smashing headlong into the planets and the forming satellites at tremendous speeds. And these collisions did a great deal to actually build our solar system and make it look like it does today. They were responsible for allowing the planets, first and foremost, to grow to their present size. It was cometesimal, small comet-like bodies that made up Uranus and Neptune, for example. It was a collision that was responsible for tilting Uranus on its side. It was a collision with a Mars-sized object that actually created our moon. Soon after the Earth formed, a Mars-sized object came and collided with the Earth and pulverized the outer layer, throwing it into space, from whence the moon, that material collected and the moon formed. And as I showed you, collisions are responsible for smashing up satellites and creating ring systems. So collisions, in fact, are the creators of worlds, and they are the destroyers of worlds. And don't forget, it was a collision that wiped out the dinosaurs and cleared the way for the eventual development and evolution of the primates, of which we like to think that humans are the culmination. Or put it another way, it would have been very hard to invent Google with a Tyrannosaurus Rex breathing down your neck. So collisions have actually done a great deal for us, and they have been a tremendous process of force in sculpting the solar system. And the craters that they create on the surfaces of these bodies can actually be studied and examined. Their morphologies can be examined to give us information about the properties of the material into which they've been placed, and to understand something of the chronology of events in the Saturn system. If you look at the distribution of craters and you know something about the projectile population, you can say something about the order of events that things happened in the system. I don't have the time to go through all that we are learning about that right now, but I am going to concentrate on two moons in particular which have stood out over the last 1,000 days. And they are Titan, which is Saturn's largest moon, about 50% larger than our moon, and then Enceladus, which is a tenth the size of Titan. Now, Titan has long intrigued planetary scientists, and before Cassini arrived there, it was the greatest single expanse of unexplored terrain that we had left in our solar system, and was believed to be, in many respects, more like its environment. Surface environment was believed to be more like the Earth's than any other that we have in the solar system. Like the Earth's, its atmosphere is very thick, and it consists largely of molecular nitrogen. Like the Earth's, its thermal structure consists of a troposphere, where the temperature decreases as you go up, and then a stratosphere, where you turn around and the temperature increases as you go further up. Like Earth's, its atmosphere has a mild greenhouse effect near the surface, so its surface is some 20 degrees warmer than it would be otherwise. But its atmosphere lacks free oxygen, and it is suffused with small but significant amounts of methane and ethane and propane and other simple organic materials containing hydrogen and carbon, which we call hydrocarbons. And for all these reasons, Titan's atmosphere was believed to be an analog, or at least the closest analog we would ever find in our solar system, to the atmosphere that scientists believe existed on the surface of the Earth prior to the emergence of life. And that's not all. The compounds, the organic materials in the atmosphere, form a ubiquitous haze. that is formed, by the way, from the breakup of methane high in the atmosphere, separating the carbon and the hydrogens. The carbons join together. They create these polymers, which end up being haze particles. Those haze particles, it was suspected, would grow over time. And they would fall over the years, over billions of years, they would fall, or at least as long as Titan had an atmosphere, would fall down to the surface and possibly coat the surface with an organic sludge. Okay? And some of these compounds, methane and ethane in particular, could be liquid at the surface of Titan, despite the unimaginable cold of minus 300 degrees Fahrenheit. In fact, what water does on Earth, methane does on Titan. It can be in the form of a solid, a liquid, or a vapor. So all of this opened up a world, literally, of bizarre possibilities. First of all, you have hundreds of kilometers of globe-enveloping haze, okay, surrounding Titan, making its days dark. High noon on Titan is as dark as deep Earth twilight here is here on the Earth. We could have patchy methane clouds floating above the surface. And in places, we might have rain, gentle methane rains falling slowly because the gravity is less than it is here on Earth. And these rains, over time, could cut gullies. They could form deep canyons. They could form rivers and cataracts and cut canyons and wash the sludge, perhaps, off the high mountains and into having the drain into low-lying basins and craters. So stop and imagine this environment for a while. You're standing on Titan, a moon in the outer solar system. You're standing on an icy surface, a water ice surface. It's very dark. It's broad daylight, but it's dark. It's cold, impossibly cold. It's misty. And before you lies Lake Michigan brimming with paint thinner. Okay? That is what we thought existed under the clouds under the haze of Titan before Cassini got there. So it was with tremendous anticipation that we looked forward to Cassini's exploration of Titan. And what we have in fact found on Titan, though different in detail, is every bit as fascinating as the story that I just described to you. And for those of us involved in this mission, it's been like a Jules Verne adventure come true. Titan's atmosphere is in fact very thick. You can clearly and beautifully see that in this image that is backlit by the sun, and you can see the rings and another moon in the background, and just one of another of our tremendously gorgeous images that we're taking around Saturn right now. But despite the haze and the impenetrable atmosphere, we do have instruments on Cassini that can see down to the surface. We outfitted our cameras with filters that allow us to see in the near infrared through spectral channels that actually allow light to penetrate through the atmosphere. And also there is a radar instrument on Cassini, which is virtually identical to the instrument that mapped the surface of Venus with the Magellan spacecraft in the early 1990s. And with all of these, we have finally been able to reconnoiter the surface of Titan, if you will, and open up this previously unexplored terrain to view. And here's what we first saw of the surface of Titan from the Cassini orbiter. First, you can see bright and you can see dark, okay? And that's what it looked like to us. Not exactly easy to interpret. For a planetary geologist to look at an image like this, the first thing they see is something linear. This looks linear. This looks basically linear. That says tectonics. There is something there that's cracking the surface in a linear fashion, like the San Andreas Fault, okay? We looked on the other side of Titan. Okay, oh, excuse me, this is a higher resolution view of the same thing I just showed you. So we see circular things. We don't see too many circular things, okay? Circular things are craters. We think maybe craters, maybe they're calderas, maybe they're volcanoes, not really sure. This looks like a caldera. We see things that look like they flowed. We see what we called pull-apart features, things that looked tectonically ripped apart, but very hard to interpret. We do see black, we do see white. Then we look at the other side of Titan, we see again, bright and dark. Even though we weren't quite sure what we were talking about, we started to call these things islands because they looked like islands, but we didn't know, were they regions that were higher than the surroundings? Were they lower than the surroundings? We had no clue. It's always a hazy day on Titan. Okay, so there's no shadows. Without shadows, it is very difficult to tell what's up and what's down. And so that left us really bereft of definitive explanations. And there was nothing that was so unambiguous, so clearly a feature or a pattern that we had seen on Earth that we could say, we understand this. We were really at a loss to know. But we did see again on this side, we saw some things that look like craters. And again, I said we call these things islands. We got to call in this Great Britain. This was Ireland. This was France. This was Iberia. This was Peloponnesia. The geography is not quite right, but it didn't bother us. We saw things that looked like they were windswept, okay? But not much else we could say. But then a remarkable event happened, and it was one that we knew would be the Rosetta Stone and help us interpret our images that we were taking from orbit. And that was about 6 months after getting into Saturn orbit came what many regard as the highlight of Cassini's explorations of Titan, a flying saucer-shaped device, which had been carried by Cassini for 7 years, was deployed to the Titan atmosphere and successfully drifted on a piece of fabric for 2.5 hours through the hazy atmosphere and came to land on its surface. This was the deployment and mission of the Huygens probe, the European-built Huygens probe. And this, I can tell you, was a positively extraordinary achievement. And for those of us in Darmstadt, Germany, at the European Space Operations Center, where this event was monitored, it was a very emotional event. It was the day that humans had landed a device of their own making in the outer solar system. It was like living science fiction. And I've come to call this a grown men crying kind of day, because grown men were disappearing into corners to have their own little private moments during this event so that they wouldn't get busted by their colleagues being seen losing it because of the overwhelming emotion of the whole event. And it was, to me, an event that was so significant it should have been celebrated with ticker tape parades in every city across the US and Europe, and unfortunately that didn't happen. But it was extraordinary for another reason, and that's because the celebratory presentations during this event were given in just a host of accents. English was used, but they were given in English accents, and American accents, and French accents, and Dutch and Italian and German accents. It was, in fact, for me, a moving demonstration of what the words United Nations are supposed to mean. And that is a group of nations joined in a common cause, and in this case, it was a massive undertaking to explore a planetary system that for all of human history had been unreachable, and now humans had touched it with something of their own making. It was a very remarkable and historical day, and certainly a day that I'm not likely to forget. I don't think anyone there will forget it. But anyway, I digress. The probe took many measurements of the atmosphere on its 2.5-hour descent down to the surface, including panoramic images. And it's hard to describe what it was like to see those first images that were released for public consumption, because it was a shock. And this is what we saw. Okay? This is a mosaic, in fact, of images that were taken as the probe descended. And we saw this region here. Okay? And it was shockingly easy to interpret. It was, as you can see, a drainage pattern that could only be produced by a flowing liquid. In fact, you can follow the channels in this drainage pattern, and they actually move away from this boundary and fall and go down here and join this tributary, and they all drain into this region right here. Okay, we know from stereo images taken during this descent, you're looking at something here that's high. This is about 100 meters higher than this area. The next picture is just, this, by the way, is taken at 16 kilometers up. This picture is taken at 8 kilometers up. Okay, you're looking at a shoreline. Okay, we weren't sure at this point, was this liquid? Okay, but you're looking at something that looks like a shoreline. Okay, now bear in mind, and islands, offshore islands. Okay, bear in mind, 16 kilometers, 8 kilometers, that's roughly airliner altitude. If you were going to get in an airline, airplane and fly from San Francisco to New York, you would be flying at something like 11 or 12 kilometers altitude. Okay? So this is the view you would have out the window of Titanian Airlines as you flew across the surface of Titan. And maybe someday someone will actually get the chance to do that. But anyway, all in all, I think, excuse me. And then here finally is the picture that we collected on the surface, the Huygens probe took once it landed. Okay, you can see the horizon in the background. You could see boulders in the front, but they look big, but they're actually no bigger than about 12 inches across. So they're like stones, almost certainly made out of water ice. These are, again, stones. They look, or pebbles, they look very well sorted. The idea is that probably some liquid flowed across this surface at one time and sorted all these stones and pebbles. But the probe landed not in liquid. It landed in what is the equivalent of a Titan mudflat, an unconsolidated ground that is suffused with liquid methane, and very likely made of the accumulation of the organic matter that I told you falls out of the sky and probably accumulated in low-lying depressions on the surface. Very much like what had been expected. So all told, the Huygens mission was a glorious success and a triumph, and gave us the kind of ground truth that helped us and is helping us still interpret our images from orbit. But still at this point, this was early 2005, there were no open bodies of liquid. We thought we'd find lots of liquid on the surface, no open bodies of liquid to be seen anywhere, not from Huygens and not from the orbiter. And still, of course, the exploration of Titan continued from orbit. We continued to take pictures, and the radar instrument continued to take its data. And it discovered another unambiguous pattern in the equatorial region of Titan. It discovered that vast regions were covered with dunes. These dunes are 100 meters high. They're several kilometers across. They go on for hundreds and hundreds of miles. There's a region that is covered 1,500 kilometers worth of surface areas, or surface extent around the equator is covered with these dunes. Okay, this is an enormous geological feature on the surface of Titan, and it indicates steady bidirectional flow of wind, or else you wouldn't get dunes like this, and obviously conditions that are dry enough to loft particles. That's how you create dunes. So not only no bodies of liquid, very dry conditions. So a great puzzle. We didn't see any liquid. We're still looking for it. Finally, Cassini got to investigate the polar regions. This was taken, picture was taken of the south polar region. That's what this cross is here. And this was the closest we got at this point to something that looked like a lake. Okay? It has a shoreline that looks like it could be a lake, very dark material inside. Okay, if you fly over Minnesota and look down at the lakes, they look black. Okay, so we thought this was probably the closest we'd come to a lake feature. We thought these other, this region here was dotted maybe with lakes. This was like a lake district. Actually, this is in absolute size the size of Lake Victoria. But if you scale it relative to the surface area of Titan, which is much smaller, it's more like the size of the Black Sea on the Earth. Okay, so this is what we saw in the South Polar region, but we didn't have any definitive evidence that this was liquid. It could easily have been argued this is just a residue. Maybe there was liquid there at one point, it evaporated, this is the residue that's left behind. We didn't have any definitive evidence. And then we looked in the North Polar region just this past February. And this is what we saw. This is our imaging data, and you could see these regions. This is a cloud feature. You could see these dark areas here. Okay, they look, again, like features we saw in the south. One of them is very large. It's as large, in fact, if you scale it, as large as the Mediterranean Sea. And then the radar got images that overlap, and they are interpreting these dark areas to be liquid because they're the darkest things that they see with the radar data. So you are looking here at where it appears the liquids have gone on Titan. These are hydrocarbons. We think you could see some of these shorelines look like the coast of Maine. And not only do we see big areas, lots of big bodies, but we see also smaller regions, a region that has smaller features in it that look like the Lake District that we saw in the south. And here we're cruising over the radar data here, and this is the pole. So it appears that the liquids on Titan, at least during the present season, which is southern summer, northern winter, have migrated to the poles. And why that should be the case, we don't know. Probably says something significant, though, about the meteorology of Titan. But all told, we have found on Titan, I think you would agree, a very remarkable and even mystical place, one that is exotic and alien, but also strangely Earth-like in its geological formations and processes, and just a fascinating place whose geologic diversity and complexity and richness is rivaled by no other body in the solar system except the Earth itself. And we will see more of Titan in the next 1,000 days of the Cassini mission. But now, in this tale of two moons that I'm telling you, we move on to Enceladus. And Enceladus is very much smaller, a tenth the size of Titan. Very bright, very white. In fact, the brightest, whitest object we have in our solar system. It's no bigger than England or the Great Britain, and I don't mean this to be a threat, just as for size comparison. But despite its size, what we have found on Enceladus with Cassini has completely thrown us for a loop. First, from a close examination of its surface, and I'm going to show you a picture now where the resolution is 10 times better than it is here, we can see a surface that doesn't look at all like the cratered, the heavily cratered surfaces of the other moons. This is a body that has obviously been geologically active in the past. It is crisscrossed by tectonic fractures at wild angles, many generations of cracks and troughs and ridges and so on. Very deep chasms, mountain folds, and so on. A few craters here and there, but otherwise a very young, very geologically active place. And the mother lode of all the discoveries that we have made on Enceladus far and away were found at the South Pole. And you're looking here. This is the South Pole of Enceladus. It is circumscribed by these mountain folds and characterized or crossed by these very deep fractures. They're about 135 kilometers across, just a few kilometers wide. This whole region is youthful. There's no craters. Obviously, does have tectonic features and folds in it. It is characterized by elevated temperatures. This whole region is warmer than the rest of Enceladus. That would be as bizarre as finding that the whole of Antarctic. The Antarctic is warmer than the tropics. I don't mean the atmosphere, I'm talking about the surface. The fractures here are different in color because they're different in composition. They are coated with simple organic materials. And then more surprising than all of that is what we saw when we found ourselves in a geometry to look back in the direction of the sun. It's what we call a high-phase geometry. It's a geometry that highlights the presence of very, very fine particles, okay? And this is what we saw. We saw that the surface from the South Pole of Enceladus, and the South Pole is right here, is emerging these jets of very fine particles extending tens of kilometers into space and feeding. If you take a picture like this and you process the faint light levels with color to bring out the contours, the faint light levels, this is what you see. These jets are feeding a huge plume that extends, in fact, we see in other pictures, extends tens of thousands of kilometers away from Enceladus. So this, in fact, was quite a surprise. It turns out, we know now that these jets of particles are accompanied by water vapor, and water vapor that is laced with simple organic materials. Okay, the analysis of all this information, other pictures we've taken of the jets of Enceladus, including the information gathered by other instruments about the water composition and the composition of the organics, all of this was put together by my team and I, and we have reached, I wouldn't call it necessarily a conclusion, but we think it is possible that these jets are erupting from subsurface reservoirs of liquid water. Okay, and if we are correct about this, then we have stumbled upon what I've called the Holy Grail of modern day planetary exploration. That is, we found an environment that contains liquid water, organic materials, and excess warmth. Or in other words, an environment that is conducive, possibly conducive, to the presence of living organisms. And I don't think I need to tell you what the discovery of living organisms or life in our solar system, should that ever happen, the kind of implications that that would have. Because if we could demonstrate that life had arisen not once, but twice, independently in our solar system, then we can infer that it has occurred a staggering number of times throughout the 13.7 billion year history of the universe. Cassini, of course, continues to orbit Saturn. It obeys our every command. It's returning magnificent image after beautiful image of a planetary system that I think you would agree now is rich in beauty and otherworldly phenomena. And I don't think I have to convince the inventors of Google Earth of the value of images of planetary bodies and of the culture-shifting power of images. Our space program has led the world in taking such images, and images that have become cultural icons. And I'm going to remind you of a couple of them. Those of you who were alert and coherent during the 1960s, I don't know if any of you were even alive during the 1960s, I was. You'll remember this famous picture taken by the Apollo 8 astronauts on December 29th, 1968. And this was a picture that had an enormous impact on Earthlings and on our perspective of our cosmic place and our responsibility for stewardship of our own planet. I think it's even credited with adding impetus to the environmental movement during the 60s. Well, 8 months ago, we on Cassini, I'm very proud to say, caught sight of something, again, that no human had ever seen before. It was a total eclipse of the sun seen from the other side of Saturn. Okay? And you can see in this gorgeous image the main rings highlighted, backlit by the sun. You could see the refracted image of the sun. This is the light being bent around Saturn by the atmosphere. You can see this, the whole system is encircled in this beautiful blue ring, which is coincident with the orbit of Enceladus. This is a ring that is the result of the exhalations of Enceladus. And if you look closely enough, and as if this weren't brilliant enough, within this impossibly lovely scene, you can spot from 1 billion miles across interplanetary space our own planet Earth, cradled in the arms of Saturn's rings. And I think it will be a long time before we see anything so moving again. I believe that nothing has greater power to alter and correct our own impression of ourselves and where we fit into the scheme of things than seeing ourselves from afar and capturing a glimpse of our own little blue ocean planet in the skies of other worlds. And that changing mindset, that changing worldview may in the end be the greatest legacy of all our interplanetary travels and the finest reward that we'll ever receive for this hopefully never-ending journey of discovery that was begun 50 years ago. Thank you. Leslie, what do we do now? Do I take questions?
Take questions.
Okay. Questions. Are there any questions? Can we put the lights up, please? Yes.
Where is the methane Titan coming from?
Oh, that's a good question. That's a $64 million question. People are working hard to try to figure that out. It's could be outgassing. That's the explanation du jour, is that it's being outgassed from the interior. In volcanic eruptions, perhaps, or somehow. And then, of course, there are those who like to think that it's bacteria on the surface of Titan that can live there and produce methane. That's another, maybe not so popular view, but that's still, there are holdouts for that point of view. Any other questions? Yes?
Is there any way that we can find these pictures?
Yes. Cyclops.org. Cyclops.org. It stands for Cassini Imaging, Central Laboratory for Operations, OPS. CICLOPS.org. That's where we post all the images that we take with our cameras. Yes?
On this picture, can you explain the image? Why doesn't the ring connect? Why is there a discontinuity there?
Do you mean this?
Yeah.
Well, okay. Okay. First, you have to know that this picture was taken, I forget now myself, it's either taken over 9 hours or taken over 6 or 3 hours. So the spacecraft was in slightly different positions when it was taking, and it's a mosaic, it's not one picture. Lots of pictures have gone into this. So when it was taking this picture here, it was in a different position than it was taking that picture there. So that's why it kind of looks funny there. But you're looking at light, you're above the rings, the sun is below. So you're actually looking at the dark side of the rings, but the sunlight is filtering through the rings. And you can see, in fact, where the rings are, well, before I get into that. This is, from here down is the southern hemisphere of the dark side of Saturn. And that looks bright because the light is hitting the rings and shining back onto the southern part of the planet. Okay, and then against that bright southern hemisphere, even though it's on the night side of Saturn, you are seeing the silhouettes of the rings here. So really, this rings here are not lit at all. There's no sunlight here at all, but this is a silhouette. So you wouldn't see anything ring-like at all were it not for the fact that you're seeing a silhouette. Okay, and then because the rings orbit in exactly one plane, that plane intersects the planet right there. So no light is getting there.
So the discontinuity right on the edge of the planet.
Here?
Yeah, all along the edge of the planet is because the rings don't connect up. That's because
That's the shadow.
that's the shadow versus the actual ring.
That's the shadow. The shadow of Saturn cast on the rings.
Okay.
Yes?
Why are the rings of Saturn so prominent than on any other gaseous planet?
It could be just a matter of statistics, that right now we're looking at, we see the solar system when Saturn happens to be the planet that has big rings around it. If estimates of the age of the rings, and this is also being debated among Cassini scientists right now, but going into Cassini, our estimates were that rings didn't live longer and weren't older than about a few 100 million years old. So to just calibrate that, back in the days of the dinosaurs, Saturn had no rings. Okay, we just happen to be seeing it now when a catastrophic disruption of a pre-existing body or maybe a capture of a body happened. It got broken apart and it formed rings. There are moons around Neptune that exist within what we call the Roche limit. That is, they're close enough to Neptune that if they got broken up tomorrow, if all of the moons within that region got broken up tomorrow, they would make a ring that was comparable to at least the A ring of Saturn. So it just might be timing when we happen to be here observing if it's true that rings are just continually created, and eroded. Yes?
What's the expected lifetime of the Cassini?
The Cassini what?
Imaging. How long is it going to last? What run out of power or fuel or navigation?
Okay, so the real limit, is politics. It's how much money the American Congress wants to give us to continue going, literally. The spacecraft is in good health. It's stabilized on gyros, and there were 4 of them. One of them was redundant. And I think one of the remaining 3 has arthritis, a little bit of arthritis. But even if the gyros went, there's still thrusters. We could turn the spacecraft with thrusters. In that case, we're using fuel, but that could still be done. So we could still turn hither and thither and take pictures. Fuel is a precious commodity. We're planning the extended mission now, so we'll almost certainly go through 2010. And then after that, we'll plan through 2012. Almost certainly by then, our budgets will be way down. There's nothing on the horizon that looks like it's going to limit us mechanically, electrically, functionally. It's just how long they'll provide funding for it to go. You know, these missions have a nasty habit of not dying. They can't even kill the Mars rovers. I think they've tried to drive them off cliffs. They won't die. So, yes.
Two questions. Do you have to pan the camera for most of the images because the light levels are low? Or like the exposure times can be short enough not to turn the spacecraft?
Oh, I see what you're saying. Okay, let's do one question at a time, because by the time you ask me the first one, I'll forget the next one. I'll forget the first. We do pan, but not really because light levels are low. It's generally we do that when we're flying so close to a body that the relative motion would give a smear if we didn't do that. So, and Cassini is an amazing spacecraft. It's been programmed so that we could say to it, point to this latitude and longitude on this satellite and keep the bore sight pointed there. And it knows that it's supposed to, you know, as the thing is turning, it does this. Okay. But for light levels, all we have to do, it's like a camera on Earth. All we do is keep the shutter open longer. And because the spacecraft is so massive, it's enormously stable. So we point it and it just stays there, and we can keep the shutters open for minutes and get beautiful images. We could never do that on Voyager. On Voyager, we couldn't expose longer than a few seconds without getting smear. So it's a tremendous improvement. That's one of the reasons why our pictures look a lot better than Voyager pictures. The other is that we're using a CCD instead of a silicon Vidicon tube, a selenium sulfur, Vidicon tube, which is what the Voyager cameras were. What's your second question?
The second question is like, what's the data rate back to Earth, and do you have to buffer the images on the spacecraft?
Oh yeah, we have to buffer, and I don't remember the data rate. Isn't that ridiculous? But I don't remember. I don't even want to say, because I'll guess and I'll get it wrong, and this is being filmed and it'll go out there and I'll forever be wrong, so I won't say it. Yes?
Are there any return trips planned to Titan's surface?
Oh, there's lots of discussion right now about what the next missions are going to be. And there's even a debate, because missions are very hard to get, especially missions of the type that we are conducting now. All the simple things have been done. So missions now are much more complex. They have to carry many more instruments. Okay, we want more data rate. We want everything more, because we want to just do a better job the next time we go out. And it takes a long time to get out to the outer solar system. So you don't want to do it piecemeal. You want to send a nice, healthy, well-equipped vehicle out there to do what you want it to do. So the big missions are few and far between, and there's always debates about what we should do next. So there's a debate going on right now. Should the next big mission be to the Jovian moon Europa? Okay, which is believed to have a subsurface ocean, but an ocean that has something like 10 kilometers worth of ice around it. Or, with the results of Cassini now, have brought the whole Saturn system to the fore as an exciting place and an important scientific place to go, I should say, in a place that's scientifically important to return to because of Titan and also because of Enceladus. If we're correct, and I have to say that's a big if, we still need to investigate this, and it needs to be looked at with a lot more detail. If we're correct that the jets are erupting from liquid water, then Enceladus has just jumped to the front of the line, in my opinion, as a body of astrobiological interest in our solar system. Because all you have to do, I'm fond of saying this, all you have to do is land on the surface, look up, and stick your tongue out. And you've got what you came for. And, you know, wouldn't it be amazing if there were microbes in those ice particles? Okay, fresh, you know, flesh frozen. So, so that would be an exciting place to go to, too. But there's the people who want to go to Europa, then there's those of us who think we should be going back to Enceladus, and then there's the people who think, well, let's go back to the Saturn system, but we really should concentrate on Titan. So there's just a lot of debate going on right now. Yes?
Is there anybody who wants a manned mission? There's so much good science being done by unmanned stuff. Why is there this push to send someone to Mars?
Well, okay, so I'm a person who obviously is deeply involved in the robotic side of things, and I'm in favor of sending humans back into space. I don't know if you read my editorial that I wrote in the New York Times, where I basically pointed out something we've all known. People have been afraid to say it, but I think it's being said more and more that the previous 25 years of the human flight program has been a waste because we've done nothing but go around and round in circles. Okay, we abandoned the Apollo program. We abandoned the Saturn V, which was the biggest, most powerful vehicle the US had ever built. We could have used it. We could have been way ahead of where we are now in the human exploration of the solar system had we not done that. And it did not cost less to go with the shuttle. It cost more in the end. So, but there has been always this friction between the human side and the robotic side. And I'm hoping that maybe soon, the twain shall meet, and even the robotic fans of the robotic exploration will see the benefit of having, at the very least, developing vehicles that would be powerful enough to send humans to the moon and Mars. We could also use those same launch vehicles to go out to visit a planetary system like Saturn. We could do very much more if we had those vehicles. I just told you the tortured path we had to take to get Cassini, 6 metric tons to get Cassini to Saturn. Okay, well, if we were going to take a path like that, but had a much larger launch vehicle, we could have carried much more than Cassini. We could have carried a Cassini orbiter. We could have carried a vehicle on the orbiter, a vehicle that could have landed on the surface of Enceladus, and a balloon that we could have deployed to Titan, to basically get blown around by the winds on Titan and investigate the surface that way. We could have done so much more. So I would rather not there be this tension, this conflict between the two. I think that I could go on and on about this topic. Okay, the NASA budget is $17 billion. That's 0.5% of the amount of money that the federal government spends. Okay, that's a minute amount of money for the whole entire agency. Okay, you could double the NASA budget and it would go unnoticed. Okay, except for those agencies that happen to be in direct conflict when it comes down to budget committees. But, put all that aside, you could double the NASA budget. It's a tiny agency, it's a tiny budget. We are a wealthy country, we could do both. Yes?
How far would it be to send a spaceship out there and bring it to back?
It would be difficult because, no, you're talking Titan or Enceladus, it matters because Enceladus is closer to Saturn, it's deeper in the gravitational well. Once you get into the gravitational well, and that takes energy, I described for you what we had to do. We had to slow the spacecraft down. You actually have to expend energy to slow down. Once you get into the gravitational well, then you got to get out. Okay, so it's difficult to do that. That would not be the very next thing we do. The very next thing we would do is send capable enough instrumentation there to make the kinds of measurements we think we need to make. If you're talking about Enceladus, we'd want to investigate the properties of the organic materials, what's called the handedness of it, to see if it's organics that has had any biological processing done to it, that kind of thing. Yes?
I was very depressed to see that the New Horizons spacecraft is a flyby.
Oh, yes.
And those of us who are alive with the first Mars flybys, where we looked and said, oh, nothing there, looks like the moon, you realize flybys are very misleading and frustrating, especially if you wait so long. So what were the arguments pro and con for that? Do it now or we're going to be dead by the time it ever happens.
I mean, there's something, I mean, that's somewhat of a joke, but there's something to be said for flybys because what would, you do have to reconnoiter the place you're going to before you for you to even know what kind of instrumentation you want to send there next. So it wasn't a foolish thing to do. It would have been nice, but it wasn't a foolish thing to do to fly by. It would be a foolish thing to do now to send flybys to Uranus and Neptune, for example, because we've already done that. The next missions to Uranus and Neptune, in my opinion, need to be orbiters. Yet there are some people who are saying, well, we're never going to get enough money for orbiters. Let's do more flybys. You see, this is the bane of living with limited resources.
Is it even technologically possible to build a two-door orbiter?
It's difficult, actually. I mean, when you say it's difficult just to get out there and.
Possible.
Oh, it would be possible if you had, enough resources. Yeah. Well, why you say that?
How big of a record would you need to
sudden.
Well, yeah, you need a big rocket to carry a lot of fuel and so on. That's, yeah.
At least fluid.
We don't have the capability now to do it. I didn't know if that's what you were saying. You know, you don't really mean is it possible. You mean is it practical? Is it presently practical? No. Yes.
So there's something that I kind of never understood about NASA, and I continue to not really understand.
I probably don't either. They don't have heated toilet seats.
Oh, that's the problem. So I noticed that most of these missions are extremely, for obvious reasons, front-loaded in time and resources and research. And then basically at the end of the day, we bet it all on like one, and if we're really lucky, two spacecraft. Whereas the actual assembly cost and part cost of the spacecraft is probably a small part, or in this case, probe, is a small part of the entire research budget. So why not launch 10 probes, and if 5 of them break, then, well, whatever. At least we don't have these incidents like, you know, we're trying to approach Mars after a 10-year project, and all of a sudden, you know, English and metric units get messed up, and oh, well, there goes 10 years and $58 billion.
Okay, I think you're under the wrong impression. The cost of the vehicles, the cost of building the vehicles, the instrumentation, okay, the cost of building all the software and so on that is used to operate the spacecraft and the instruments is way more than we have for research. That is the vast bulk. I mean, this is for the scientists involved, this is always a tremendous frustration. We have budgets that allow us to take pictures, archive them, put them in the Planetary Data System Archive, and very little money to actually do research. So that's where all the money goes.
Oh, sorry, by research I meant the whole R&D and engineering effort of actually designing the spacecraft in the first place. So that the idea would be, and maybe I'm totally wrong here, but it just seems that the cost of the physical craft, once you've done all the engineering work and all the software design, is essentially very small compared to the entire project. So why not launch 10 probes instead of one?
Well, I think you may be wrong about that, but that's a philosophy that had been followed. In the early days of NASA, there was always redundant spacecraft because they always expected one to go belly up. But we don't do that anymore because the spacecraft are getting more and more complex, and there is some recurring costs for building, you know, a second, a third, and a fourth. And besides, you got to operate those too. It's a very expensive. I mean, it's expensive in people time, and that's really where all the funding is. So, yes.
Just to follow up on that question, if NASA developed a craft and launched it today, what would be the additional cost as a percentage of the first craft to launch another craft of exactly the same thing with just say one line of code changed?
I'm sorry, I don't know the answer. I don't know the exact number.
These are really custom jobs. These are really custom jobs. I've been at JPL with exactly stuff. It's really, it's not an industrial line process at all.
That's right, but
I didn't hear what you said. It's really a what job?
It's a custom job.
Custom job. Yeah, that's right.
And it varies from, you know, like target to target.
Well, okay, so there were good intentions. The Cassini spacecraft was supposed to be, there was a mission called CRAF, Comet Rendezvous Asteroid Flyby. The CRAF mission and the Cassini mission were supposed to be identical spacecraft. It was called the Mariner Mark II spacecraft line. They were going to build lots of these vehicles, design them, and then just send one to Saturn, one to a comet, one here and one there. And then, as always happens, budgets get cut, and so you're back just building one. In fact, the CRAF mission got canceled. So it's a good concept, but I think it's just because things are getting more and more complex, it ends up being custom because you only have the budget for one.
And there's a lot of testing going on as well. It's not cheap like we should, but there's a lot of QA going on there.
Any other questions? Okay, well, thank you for staying so long.